Component.
Part of. Hope everyone has gone through the notes, and I hope you have solved at least some 10-15 questions. So last thing we are doing diodes in reverse bias and forward bias. Let's go ahead with that. Next thing is a Zener diode. Again, just to brief you a bit, what is a Zener diode? So when you take a diode and if you have a high doping, the width will be very small, so it generates a high electric field, and there will be a dielectric breakdown, and this makes it suddenly the region becomes conducting. So if you look at the graph here, once you reach a certain voltage, there will be a breakdown and there will be a huge surge of current. In this process, current can change, but the voltage remains constant. That's what was happening. So how will the frame questions on Zener diode? Again, it's really not that difficult. Like if you see in forward bias, it is in wire, reverse bias, it is an open circuit. So in a breakdown, now this is the important thing. They'll ask you questions on this. A Zener diode will work in what bias? It works in reverse bias because need to get a breakdown. It is also used as a voltage regulator. So meaning if you keep anything in parallel, the voltage will remain same. So let's see this thing. So look at this thing. So this Zener diode ka breakdown voltage is 10 volt. So anything that you keep in parallel will maintain 10 volt. That's it. That is only concept. Once you're got that, it is simply a current electricity equation. So let's redraw the circuit. $50 volt, 10 ohm, 5 ohm. So this Zener diode will give you 10 volt ka voltage. If this is 10 volt, then this is also 10 volt because they're in parallel. Now, if this is 10 volt, then this should be 40 volt. Why? Because the total is 50, 40 plus 10. That means the current in this branch will be 10 by 5, which is 2 ampere. Then the current in this branch will be 40 by 10, which is 4 ampere. Then where is the balance current going on here? So the current in the diode here will be 4 minus 2, 2 ampere. Got it? So if they ask you current in the diode, don't say V by R. It's a blunder. There is no resistance for the diode there. You can't apply Ohm's law for every damn thing. Getting it? So for a diode, there is no way to figure it out directly. Only for a resistance, you can say V by R is current. Make sense? That's it. So once you know what is the voltage, you just solve it like a regular circuit. Now you guys try this. We have a 100 volt battery, 15 ohm, 5 ohm, and a diode of 20 volt breakdown. Find the current in the diode. Second case, if the battery ka voltage is 30 volts, then find the current in the 15 ohm. Two different questions. That's it. A Zener diode will simply maintain a voltage. Once you're done with that statement, it is a current electricity question. Let's see. Yeah, I think most of you got it. So let's read this again. So be careful. This should be in reverse bias. So this was like a higher voltage. If you see, this is 0, this is plus, this is minus, this is P, and this is N. This is 15 ohms. This is 5 ohms. Breakdown is 20 volts. So this is 20. Then this will be 80 volts. And then current in this branch will be 20 by 5, 4 ampere. And the current in this branch will be 80 by 15, 16 by 3 ampere. So the balance current in the diode will be 16 by 3 minus 4, 4 by 3 ampere. Clear what we did? Now in the second case, you are applying voltage 30 volts. So this is something you need to always check. Forget about the diode for a moment. If you take 15 and 5, the voltage will divide in the ratio of 3:1. So this will actually get a voltage of 7.5 volts. This is less than the breakdown voltage. That means, diode will not even get activated. It will act like an open circuit. You're getting it? So the breakdown voltage of a Zener diode is 20 volts. 7.5 volt is less than the breakdown voltage. So just because you see a Zener diode, don't always put a constant voltage. Ask yourself, is the voltage trying to exceed that breakdown voltage? Is less than breakdown voltage of 20 volt. Therefore, it won't be activated. It will be just a reverse bias circuit, so open circuit. So when it gets activated, it kind of becomes like a constant voltage source, but that's it. So that is kind of useless. So the current I will be 30 by 20, 1.5 amperes. Check. So be careful with that. So there is no guarantee Zener diode will always work. It should exceed the breakdown voltage, then it will make it constant. Clear with this? Any doubts on this? Let's see one more. Get this? Next thing. Oh, yeah, I think, yeah, it's one. So if this is 10 volt, this is 10 volt, so this will be 2 ampere. If you get confused with the voltages, let this be I, then this will be I minus 2, and this will be I. I can apply Kirchhoff's loop law. Kirchhoff's loop law doesn't care what element is there. You can always apply it. Resistor, diode, inductor, anything. That will be 100 minus 25I minus, that is 10 volt, which is 5 into 2 minus 5 into I. You came back to initial. That would be 90 is equal to 30I. Easy. Okay. Now let's see a few more questions. Now, if you have seen, I have sent you a file. You know, these old PYQs are there 20, 21, and 22. So I have taken out some good ones from there. So make sure to finish your PYQs for these chapters. That is sufficient. Let's see some questions from there. All these are JEE Mains questions last 3-4 years. Get this. Let's see. Just read out the circuit. You have to draw them, but diode is forward biased. It has a voltage drop of 0.5. That must be the barrier potential. Battery is 1.5. You kept a resistor. This guy eats away 0.5 volt. This is R. And is also saying the diode cannot take more than 10 milliampere current, so 0.01. So if that is 0.5 volt, this is 1 volt, and the current is 0.01. Done. Resistance is voltage by current. Now, how easy was that? But people go for and come because they don't understand, like, oh, diode resistance. They get scared the moment they see that. Anyway, it won't be so lucky. Every time it won't be that easy also. So let's see one more. This is a theoretical question. Let's see how many of you remember this. Now, if you see this question, right, the moment you see extrinsic semiconductor, Fermi level, doping, your brain will fuse. So if that's what I'm saying, if you don't know the words, right, you will feel like, what the hell are you even talking about? If you see, even in the last class only, I must have introduced around 12 new words. Barrier potential, valency band, conduction band, Fermi level. Getting it? There were a lot of new terminologies. So what is this Fermi level? Again, just to brief you up. Fermi level is the highest occupied level by the electrons at a 0 Kelvin. So what is an extrinsic semiconductor? You add impurities to increase the conduction. Now in a p-type, what are you doing? In a p-type, you're adding extra holes. Matlab, the lower holes are nothing but vacancies. Matlab, lower bands mein you're creating vacancies. Logically, so if you have vacancies in the lower bands, electrons will start coming down. Then your highest occupied level will decrease. In case of an n-type, you're putting extra electrons, means they will occupy more and more orbits, means your highest level will increase. Got this? That was the whole explanation. So based on that, what will be the answer then? B, na? So I'll just put that solution here with the detailed explanation in there. Now, if you know actually what you're talking about, it'll take basically 20 seconds to solve the problem. Because you don't know your terminologies in the question, you lost 4 marks. Clear? Let's see one more. No, it's not like everything is easy also. There are some good ones. Let's see this one. The reason why people find it tough, if suppose if we had done this chapter in May, 6 months back, till now you would have written, questions on this thing in at least 5 to 6 days. By then you would have thought like it is normal. The problem ये होता है, this is not there for advanced, this is for mains, and we always do it in the end, right? If not this some other chapter, no matter which chapter I do in the end, now what will happen? You won't get enough time to practice. Revision will start. Your classes made some revision will go on. That last 1-2 months that you're so busy, this thing will go for a toss. And then sudden, that is the reason that things feels little difficult. Let's get this. These are actual JE questions, huh? So think for a minute or so, then I'll show you. Let's see. First of all, let's understand what is given in the circuit here. This thing, when you see this picture, this only must have blown your fuses. Like, what the hell is even that figure looks like? It is actually two diodes placed for facing each other. Because first time when I saw this question, I was like, what the hell is that actually? That, and then you carefully see that, you'll actually realize there are two diodes there. So this is one Zener diode. They could have just given a little more space, but you can. So what is the catch here? So when you're giving this is plus and this is minus, this guy will be in forward bias. So a Zener diode in forward bias is just a wire. This will be in reverse bias. When you give this minus and this is plus, this will be in forward bias and this will be in reverse bias. So always at any point, one will become like a wire and one will become a reverse bias. Okay. Now, if you look at the output here, you are giving voltage from 0 to 10. So when you give voltage, let's say when the voltage is between 6 and 0, your voltage, this is less than breakdown, isn't it? What is the breakdown voltage given? 6 volts. So if you give anything less than 6, the forward bias will act like a wire and the reverse bias will become an open circuit. So Zener won't be activated. And if the Zener is not activated, it will just be an open circuit. There will be no current flow in the circuit. Then you get V output will become equal to V input. So whatever input you are giving, that only will come as an output. But once you exceed 6 volts, Zener will have a breakdown. And once the Zener gets activated, what it will do? It will not let the voltage increase. The same thing happen in the forward bias and the reverse bias. So there'll be always one guy who will be activated. So now the voltage becomes 6 volts if you exceed 6. So now if you try to plot the graph, so up to 6 and minus 6. So you will increase input is equal to output till 6 volts, and after 6 you become flat. Then decrease again till minus 6. Then again you become flat. Increase again, become flat. So basically this part of the graphs will get cut off. The ones I'm shading here. So any voltage more than 6 will not be there. This is the 6 and this is your minus 6. Clear with this? There is a sine function where 6 to 10 is cut off. Now got this. There. That is the idea of this thing. So when you put a Zener diode, anything less than the breakdown will act like a reverse bias, but once you exceed, it will become a this thing. Any doubts on this? It's a good one. You have to think of it. Let's see one more. There. This is another way of asking a question. Every time they won't give you A and B. Look at this graph here. How to read this graph. He's saying A ka input is given by this graph. So what is this binary? When you're on, 1. When you're off, it is 0. So what do you mean by on? If you have a voltage. So 0 to 1, there is a positive voltage. So it will work on 1. 1 to 2, positive voltage 1. 2 to 3, there is no voltage, means 0. 3 to 4, there is a voltage 1. 4 to 5, there is a voltage 1. Are you getting how to read that graph? Means A ka input is 1, 1, 0, 1, 1. So 0 to 1 second you get 1. Similarly, if you look at B, initially there is no voltage 0. Voltage 1, 0, 1, 0. So indirectly he's saying if I give you input 1, 1, 0, 1, 1 and 0, 1, 0, 1, 0, the output will look like what? Are you clear how to read these graphs? Now, can you tell me what will be the output graph look like? This is another way of asking logic gates. Every time they don't give you values, they can give you a graph. Let's see. So first of all, let's get the Y value. So if you give A to a NAND gate, you'll get an A bar. So basically it behaves like a NOT gate, and this is B. This will be A bar plus B, and this is A bar plus B ka whole bar. So indirectly, the final output is A dot B bar. So A, B, B bar, and you want A dot B bar. So A ka input is 1, 1, 0, 1, 1. But you don't want B, you want B bar. So take A ka values and take B bar ka AND gate. So these two ka AND gate. 1 and 1, 1, 1, 0, 0, 0, 0, 1. So your final graph will look something of this sort. So 0 to 1 second, it will be on. Then it will not work till 4 seconds, and then it will again work. In the exam, right, it is easy to eliminate graphs. You can actually check any one input and see what it is coming out. That would be faster. Drawing the graph is little takes time, but eliminating is much faster. Clear with this? So that is another type of asking based on the graphs. Let's get this. So this is a regular one. What is Y here? Let's see. Where do we have? Here is Devansh. That is wrong. Nee, Boroja. Right, Ishana. Right, Ansh. So this is A, this is B, this is A, this is B. A dot B whole bar is A bar plus B bar De Morgan's theorem. A dot A bar is 0. B dot B bar is also 0. This is an XOR gate. Clear? That so you should be able to simplify that. That's important. Next one. This is another good one. So they gave two diodes here. So A and B are inputs. So the question is, what is this gate? The output Y represents what gate? Let's see. Now this thing you have to be little careful. Let me show you something. So if you just take one diode here, now if it is exam, see how I will do. Let's just dump, let's say if I put 5 volt here, 5 volt means on. If this is 5 volt, right? This is 5 volt and there's a resistor, so it can be 5 or less than 5. So this will become reverse bias, isn't it? If that becomes reverse bias, meaning this will become an open circuit. If that is an open circuit, meaning current will not flow. If the current does not flow, then this is 5. So this is also 5. Okay? But let's say the other one, you keep 0 volt. If you keep this 0, this is 5, this becomes a forward bias. If this becomes a forward bias, meaning this will become a wire. And if this is a wire, and if this is 0, then this also will get shorted. This also will become 0. Means even if one of them is 0, it will get shorted and become 0. If both are 0, then it will get be 0. The only time it will work is when both are on, isn't it? Now you tell me which output will give you on when both are on? AND gate. So this thing is behaving like an AND gate. So, but anyways, let's see. So if this was 0 volt, this was 5 volt, then this will be in forward bias. If this was in forward bias, and then this thing simply becomes a wire. So if this was 0, then this also will be 0, then Y will be 0. So even if one logic gate, if one input is 0, the wire will get shorted. But if you give 5 volt here, this is will become in reverse bias. Then it would look like this, and nothing is there to open up. So this is 5 volt, this will be 5, so Y is equal to on. So if you look at this, so A, B, and Y. So if both are 0, 0, Y will be shorted, 0, 1, shorted, 1, 0, shorted, 1, 1, on. This is an AND gate logic gate. So clear? Tricky? So not tough, but it is tricky. If you don't realize what you're doing, you will goof up. Clear with this? There, with the diodes, this is how you actually create an AND gate with the diodes. So I gave you that analogy of two, things in series and all, but this is how it is manufactured. Let's get this. Zener diode. Again, I have taken up some questions from that material, so make sure to do your PYQs. So the power of the is asking for the power. Now here one thing I'll tell you. If they ask you find the power, don't say I square R. Getting it? That's a blunder. power, getting it? So for some reason, right, people I see, what is current V by R? What is power I square R? Like this is what people keep saying. So power in a diode, so power in a battery is voltage across the battery into current in the battery. Power in a capacitor, voltage across the capacitor, and power current in the capacitor. So voltage across the diode. So this is 15 volts. So this current will be 1 by 6 ampere. If that is 15 and this is 22, this is 7 volt and this will be 7 by 35, 1 by 5 ampere. So the balance current will be 1 by 30. So therefore the power will be, the voltage is 15 by 30, that would be 0.5, which is 5 into 10 power minus 1. Easy? Clear? Let's see one more. Let's get this thing. So here, if you see the word here, na, the maximum Zener current means you can take the current from 0 to 10. So first assume current is 10, find the resistance, then assume the current is 0, then find the resistance. So you have to do it 2 times. In both the cases, you'll get 2 different RLs. So and is asking the ratio of that. So the catch is that since he said maximum Zener current, it could have been anything. See, the only thing Zener will maintain the voltage. Current could be anything it wants. Now try. I'll give you a minute. Right, Ishana. Yeah, I think most of you got it. Right, Saish. Nee, Ansh. Nee, Poroja. Right, Pratik. Harika. Right. Let's see. Just you have to read the circuit. So initially, take this as 10 milliampere. If that is 8 volt, this is a 2 volt. Then this guy will be 2 by 100, 20 milliampere. If that's 20 milliampere, then this will be 10 milliampere. And the voltage is 8. So R will be 8 by 0.01. That's 800 ohms. In the second case, this time you take the current to be 0, but the voltage is there. So this will be 2 volt. Then this will be 20 milliampere. Then all the current goes here 20 milliampere. But this is still 8 volts. So this time the resistance will be 8 by 0.02. This is 400 ohms. The ratio is 2. Clear? So the word is this. This is the maximum. So minimum is 0. So you take the two extremes, that will give the two extreme values of resistance. Easy? I'm telling you, once you understand what it does, then it becomes pretty easy to solve, but it doesn't click in the exam. That's what I'm saying. Practice. Finish off all the PYQs from 2020 to 25. That much is sufficient. You'll be able to handle. Because एक question तो पक्का आएगा. One question that definitely it will come. That's a little about the diode and stuff. The next thing. So if you see, the one major application we saw so far is a Zener diode, which is a voltage regulator. It will maintain a constant voltage. The next application is a rectifier. Again, a new terminology there. So what is a rectifier? It converts your AC into DC, basically your mobile phone ka adapter. So it takes AC current and charges your mobile or your laptop, which is DC based. Generally, it converts into 12 volt ka DC. Your laptops and your mobile phones, right? They get charged at 12. So the first thing is an half wave rectifier. This is also important for your boards. So just have an idea there. So this is your transformer. This input is V0 sine omega t. So what we do, we take the voltage across the load as an output thing. So the potential across the load resistance is your output. Now see what happens. When the input is in a positive cycle, the diode will be in forward bias. So it will let the current pass and there will be voltage across the diode. When it is in the negative cycle, the diode will become reverse bias and the current won't flow. The problem is, if you remember how we defined DC, anyone remember the DC ka definition and AC ka definition? AC ka definition is if the voltage of the current changes periodically. DC ka definition is the sign does not change, but magnitude can, vary. So if you send an input like this, you will see, you will get an output like this. It will be on for the positive cycle, off cycle, it doesn't work. Again, it will on, it again doesn't work. So technically, definition wise, this is DC only because the sign doesn't change. But you actually lose a lot of energy in this. So for half of the cycle, it doesn't work. That's why it is called an half wave rectifier. The current flows only in the forward bias in the positive cycle. And here, if you look at the frequency of the output, this is the frequency of the input because the time period is same. This thing repeats only after time t. And this thing has a maximum efficiency. Again, this is just a result of around 41.2%. So you lose most of it. Then we have a full wave rectifier. So if you want to rectify the full wave, we use two diodes. This is your output. This is your center tap. Remember, potentiometer we used to have the jockey, na? Something of that sort. So we have two diodes here, D1 and D2. Now see what happens. When you're in a positive cycle, this is plus, minus. This will be in forward bias, so current will flow like this. So this guy will become forward bias and this guy will become reverse bias. So D2 will not work. When the cycle reverses, minus, plus, minus, plus. Now this becomes forward bias. So one of the cycle, it will always work. So now this will become reverse bias and this will become forward bias. If you send an input like this, your output will look like this, like a mod sine function. So in the positive cycle, D1 will work, negative cycle, D2 will work, D1, D2. So, and if you look at the time period, it becomes T by 2. It repeats after every T by 2. The periodicity has become half. And the frequency of the output will be 2 times the frequency. This was a question in the exam once. They said the frequency of the input is 50 hertz. What is the frequency of the output in a full wave rectifier? Simple question, tha. But the moment you don't know what is full wave rectifier, you will be gone. Maximum efficiency is around 81.2%. I think this is 40.6%. That is just a number from NCRT, so don't worry too much about it. There's no proof or anything for this. But this thing full wave rectifier, right? The thing is that center tap is a problem. If that moves or if that thing is moving continuously, it will create sparks and all. So we don't want to have any moving parts. So we have a better design. We call this thing bridge wave rectifier. There. We use 4 diodes, D1, D2, D3, and D4. This itself is a question in the mains level. Which of the following is a bridge wave rectifier? Now see what happens. When this goes in a positive cycle, current will go here, D1 is in forward bias, goes through the load, D4 is in forward bias, comes back. So D1, D4 will work. When this is a negative cycle, D3 is in forward bias, D2 is in forward bias, this will work. Getting this? So either way, it will always work out. So the output will be same as the bridge wave rectifier. That will be D1, D4. This will be D2, D3, D1, D4, and so on. So D1 and D4 will be in forward bias. In a positive cycle. D3 and D2 will be in forward bias and negative cycle. So there are no moving parts. That is the only thing. So technically, this and the full wave rectifier are one and the same. And the frequency of the output is 2 times the frequency of input. But again, if you see, right, this mod sine ka thing, yeah, technically this is AC, but when this is DC, but when you say DC, right, we are not looking at this. We want something constant, isn't it? So what we do, we take the bridge wave rectifier and we do something interesting. Take a bridge wave rectifier and put a large capacitor in parallel to the load resistance. What happens? Now, when you're charging, capacitor also will get charged. But when the negative cycle mein current is trying to decrease, what will the capacitor try to do? It will try to maintain the voltage. It will try to discharge. Okay. So the capacitor discharges to maintain the current. And now, why large capacitor? If you have a large capacitor, what is the time constant? RC. If you have a large capacitor, you have a large time constant. Now understand, what is the meaning of a time constant? The time taken to decay by 63% in one time constant. Now let's say time constant is 1 second. And here your frequency is 50 hertz. Matlab, in 1 by 50th of a cycle, your current is increasing and decreasing. Now compared to 1 by 50, 1 second is pretty large, right? Then 1 by 50 seconds, what do you think will happen to the capacitor? It will go from 100 to 98% or 99%. By the time it goes to 98%, the battery will again become positive terminal, capacitor will again charge. You're getting it? So the time interval becomes, this fluctuation is so small, the capacitor will not have time to discharge only. So it will try to maintain almost a constant voltage. So maintaining a large time constant is important. A large time constant, voltage almost remains constant. So you will see fluctuations, but it will be too small. You won't even notice it. If you put a very large capacitor, then it's like this. You won't even notice the difference. So larger the capacitance, the lesser the fluctuations. So even though when your adapter set is giving 12, it is maybe giving 12 plus or minus 0.2. That much fluctuations your devices can handle. This is what happens in your adapter. Clear with this? That's about your rectifiers. Then, so this is your second application. First thing was a voltage regulator. Second thing is a rectifier. Xenon diode is a voltage regulator. Next thing is a photodiode. What is a photodiode? Basically, it is your light sensors. So when you put your hand between the lift, the doors open. When you go to the washroom and put your hand, the water comes out. All these are, basically the light sensors. These are also based on diodes only. So how does this work? So you take a diode and you operate this in reverse bias. So this itself is a question of photodiode works in what bias? It operates in reverse bias. So what happens exactly here? So here what we do, we maintain the sensors very close to the breakdown voltage. Let's say the breakdown voltage is 10 volts, you try to operate them at 9.9. The diode is operated near the breakdown voltage. So let's say this is your breakdown voltage. So you operate somewhere here. So then what happens? All you need is a little light. So when the light comes and falls on the PN junction, so that will emit your photons. It's like kind of like a sort of photoelectric effect that will provide you that extra voltage required for the breakdown. Means think about this. When you are in less than breakdown, you act like an open circuit. Current won't flow. The moment the light falls, suddenly the circuit becomes a breakdown and there's a current starts flowing. It becomes like a wire. So suddenly the circuit becomes on. So that light is becoming like on and off. You put your hand, you cut off the light supply. When you remove the hand, light falls again. So it is on. Getting it? So you can make the current flow and current stop by just blocking the light there. So if you look at your lift also, right? If you see, actually there are two infrared sensors there. There's an infrared light passing through that thing between the doors. So when you're putting your hand, what you're doing is actually you're cutting off that infrared beam. You can't see that, but it is there. There's an infrared beam there. Or else think about it. When you put your hand, how does the lift know that you kept your hand in the middle? You're disturbing something, no? That is how it knows. So when light is incident, the depletion layer, the electrons emitted push the diode towards breakdown. Again, I'm putting it in a very simple form. The devices are much more complex. They take many more things. Meaning, if you just get a, if a mosquito starts flying, I don't want it to open, isn't it? So basically, if there is no light, it will just be like an open circuit. This is your third application, the photodiode. First was Zener diode, voltage regulator, rectifier, photodiode, which is light sensors. The next thing is your solar cells. Now again, solar cells is not much. The one question is solar cell works on what? No bias. It doesn't work in forward bias or reverse bias because this itself actually produces the voltage. There's not much on this. I should just know the picture there. So there. So light falls on the PN junction and that will emit the electrons. So that itself is used as a battery. And when you try to plot the current versus voltage, so the diode is acting like a battery. It's an open circuit voltage. So if it's an open circuit, there'll be voltage, but there'll be no current. If you short this, there'll be no voltage, but there'll be current. So it can have some internal resistance. So the graph is important and no bias is important. That's it. There's nothing much on solar cell. The graph was actually asked in one of the year. And the fifth one, LED, light emitting diode. So actually, if you see diodes, you actually been hearing about it, you just didn't notice it. So all the light sources that are in your house, your TV, your screen, everything is based on these LEDs only. How does these things work? So these things work on forward bias. So photodiodes are in reverse bias, solar cells is no bias, LED is in forward bias. It's a pretty straightforward idea there. So when you put it in forward bias, the electrons will start jumping into the holes. Again, what is a hole? Hole is nothing but absence of electron in the valency band, which is a lower orbit. And electrons are jumping from the conduction band. So when electrons jump from higher to lower orbit, what will happen? You get photons. So the depletion layer, right, this region will start giving you photons. So basically you are letting electrons combine and this electrons will again come back from here. Again, you'll jump into the holes. This is a continuous process. And the difference in energy level will give you different colors, different wavelengths and different colors. So I think in 1950s and all, no, the first LEDs created were infrared LEDs and red LEDs. These are easy to create because red ka wavelength is high, so the energy level is small. Then within few years, right, they got yellow LEDs, green LEDs, everything, but they couldn't create blue LEDs. Meaning the blue LED ka energy level was so high, and whatever they did, they're failing. People at one point, right, they thought creating blue LED is a myth. They couldn't create. Every major company in the world, right, were literally pouring, lots of money for research and creating a blue LED. Simple reason: you have red, you have green. RGB color, suna na? These are the three primary colors. If you don't have blue, you can't create white. Without blue, you won't get the colors. Matlab the TV screen you're seeing, the colors what you're seeing wouldn't have existed without the blue LED. Kidding? So blue LED was like something else only. Finally, Japan, in a Japanese company, right? He was an employee. He was not a researcher or something like that. He was an employee. He was working on all these things. He's a researcher, but he's not as alone or something. He's working in an employment. So that guy did a lot of work. Like the company almost gave up and said, "Boss, chhod do. Matlab, it's not going to happen." And this guy shifted everything to his house and he started working and everything. I think somewhere in 70s or 80s, almost I think 15, 20 years ke baad, they could create a blue LED. And it was such a big thing. Now, normally they don't give Nobel Prize for this kind of stuff, but they gave a for a Nobel Prize for a blue LED. Because the kind of impact it had on, the everything, it was huge. You should check it out in YouTube when you have time. Na? Just search blue LED and you will get a lot of pretty nice videos on that. So if we had no blue LEDs, there will be nothing called color so far. Like things would be pretty weird. You have red, green, everything, but no blue. So your all your colors will be in red and green shaded. So when you try to plot current versus voltage graph, since the red has a lower wavelength, its cutoff voltage will be small. So you need to get at least this much voltage before the light comes out. Then green will take a little more voltage, and then comes blue. That graph is also important. They'll give you three colors and they'll ask you which of the following is right for an LED. Clear with this. That's about your semiconductors, right? So you can finish off now. You'll be able to handle most of it. So do start solving your PYQs on this, right? And mostly next week I'll keep an exam also on this thing, semiconductors. If you just finish your PYQs, it'll be more than sufficient. You'll cover a lot. And if you want to read something, you can read NCERT for these chapters. Just if you want, you can just take the book and read once for semiconductors and magnets and all. That is about the semiconductors. The next thing is the magnetism. Let's have a small break. Come back by 9:48. 9, yeah, and then we'll continue from here. Chalo, I'm Sonny. Let's start off. So much theory, na? Great. Next thing, magnetism. Now, in this, we have two parts. One is your bar magnetism, and one is magnetic materials. Bar magnetism will look something similar to electrostatics. There are a lot of resemblances. You'll see. Other scams on. So let's see. First thing is your bar magnet. So when you take a magnet, you have a north pole and the south pole. So we define something called small m. The small m is called pole strength. And 2L is the length of the magnet. We use 2L. You will see later on. It makes your equations look better. So small m is called pole strength. Pole ka strength means it tells you how strong the magnet is. This is quite similar to charge. Just like charge tells you how strong the field is, so bigger the charge, more stronger the field. 2L is your length of the magnet, which is the distance between the poles. So here we define something called capital M, which is magnetic moment. So be careful, capital M, small m. So magnetic moment is simply the pole strength into distance between the poles. So this is small m into 2L in this case. Now, if you remember, in magnetism, we studied magnetic moment mu bar, which is NIA. This is also magnetic moment only, but this is a magnetic moment due to current loops. So for current loops, we call it a mu bar. For magnets, we call it capital M. And technically, there's no difference between them. If someone says a magnet has some 10 times you 10 into something, and mu bar is also 10 into something, you can't tell whether it is a magnet or a current carrying coil. That means if you have a current loop, you can replace that with a magnet of capital M, which is mu bar. This is important. And if you notice here, there is some resemblance here to a dipole. If you take a dipole P bar, this is nothing but plus Q minus Q. And the P bar is nothing but Q into D bar. So if you see a bar magnet looks similar to a dipole. So we can actually use this logic to compare, and you will notice there are a lot of similarities. So if you see in electrostatics, if we have a charge Q at a point P, so we call this thing magnetostatics. So technically speaking, you cannot get a pole, a single north pole, a single south pole. But as long as the equations look same, Max doesn't care. So we can say something like that. So plus M, we have the pole strength. We also call this thing as magnetic charge. It resembles. Now look at the formulas. What is the electric field due to a point charge? 1 by 4 pi epsilon q by r square. So what is the magnetic field due to a pole strength? So wherever there is epsilon, it becomes 1 by mu naught. Mu naught by 4 pi. If you remember, we have seen this in Biot-Savart's law also. Mu naught by 4 pi q ka place mein small m by r square. The formulas work mathematically. What is the electric force? Charge into field. What is the magnetic force? Pole strength into magnetic field. So electric field becomes magnetic field, and charge becomes pole strength. Dipole moment is q into d. Magnetic moment will be m into 12. This analogy will be quite useful. So basically, whenever you see k ka value, which is 1 by 4 pi epsilon, you can replace this with mu naught by 4 pi. Electric field will become magnetic field. Charge q will become pole strength. Dipole moment becomes capital M. So literally everything that you studied in dipole moment will come. So all the formulas you did in dipole and everything are valid. In case you forgot, you should go back to electrostatics once. So if you take a dipole and if you take a far off point, angle theta for r much greater than d. Hope you remember the results. What is the electric field result? 2 kp cos theta by r cube, r cap, kp sin theta by r cube, theta cap, the radial direction. If you have a dipole and if you have an electric field at an angle theta, we know torque is equal to P cross E bar. Potential energy is equal to minus P bar dot E bar. I can do the same thing here. Instead of a dipole, I can take a magnet. Can you tell me how will the formula change? 2 will remain 2. K becomes mu naught by 4 pi. P becomes capital M. R cube cos theta. R cap. Get it? How did we write this? So there's no need to derive again. Everything will look same. So if they ask something about the magnet, you can think of your electric dipole. You can solve that and you can bring it back here. Mu naught by 4 pi. M sin theta by r cube. Again, this is valid only when your distance is much greater than 12. Similarly, if you take a magnet and put it in a magnetic field, we get torque is equal to m cross b. The potential energy becomes minus m dot b. If you remember, torque on a current carrying coil is mu cross b. Mu becomes m bar. Clear with this? Then these are some standard ones. So when you take a dipole on the axial line, the field is 2 kp by r cube. They would have straightforward questions on axial line only. Basically, this is theta is 0 degrees. This is your axial line. So sometimes they'll ask a question like this. If there are 2 points A and B, one on axial line, one on the equatorial line, it is observed the field ka magnitude is same. Then find the ratio of the distances. So you just need to know the formula. This will be Kp by r cube. So it will be like Kp by r1 cube is equal to 2 Kp by r2 cube. If you equate them, you'll get r1 by r2 ratio. Similarly, dipole-dipole interactions. Yeah, the formulas. We did it, dipoles pretty extensively. You should go and check it out in case you forgot. Because everything you did, you can just put a magnet and it works. P1 bar, P2 bar. The force is minus 6K P1 P2 by R power 4. Potential energy is minus 2K P1 P2 by R cubed. So I can do the same thing here also. So the formula becomes 2 mu naught by 4 pi. There. Same way, we can even get here magnetic interactions. So if you take two magnets, again, remember this is when they're very far. The force becomes minus 6 mu naught by 4 pi m1 m2 by r power 4. This is 3 actually. Clear this? Any doubts on this? There, you can see all these are just the formulas there. Then, let's see a question. This was a CT question. You have a magnet of magnetic moment, capital M. Now someone bent this into a semicircle. Find the new magnetic moment. Let's see. Yeah, right, Saish. So initially the magnetic moment m into small m into 2L. So when you bend a magnet, what remains constant? The length. So the 2L length becomes pi into capital R. Let this radius be R. So the new magnetic moment will be the pole strength into, remember the formula, the distance between the poles, it has become 2R. So if you actually make it into a full circle, the magnetic moment becomes 0. This will be m, and what is R? R is 2L by pi. But m into 2L is capital M, so it will become 2 capital M by pi. Central mass का formula जैसा लग रहा है ना? There, so you can bend it into any shape. They can bend it right angle, triangle, something. So be careful. The definition is simple: pole strength into distance between the poles. Done. That is bending of magnets. So when you bend magnets, magnetic moment changes. What happens when you cut a magnet? There are two ways you can cut the magnet. You can cut it vertically or you can cut it horizontally. Let's say I'm cutting it equal pieces. So when you cut it vertically, the piece pole strength will remain same. The pole strength doesn't change, but the length becomes half. So the new magnetic moment becomes m into L, which becomes m by 2. So the overall magnetic moment does drop. When you cut it horizontally, the length remains same, but the poles become half. So the magnetic moment will still become half, but the reason is different. So based on this, if I ask you a question like this, suppose if I have a magnet whose magnetic moment is m, let's say you're cutting it vertically, equal pieces, p times vertically, and let's say you're cutting q times horizontally. What will be the magnetic moment of each piece? Identical pieces. Then what will be the magnetic moment of that one small piece? Maybe, Han. Maybe, Purvaja. Be careful, be careful. It's a simple trap. Nee, Ahana. Right, Purvaja. Let's see. If you cut one time, how many pieces you get? Two pieces. If you cut two times, how many pieces you get? Three pieces. If you get p times, how many pieces you get? You get p1 plus p plus 1 pieces. So this guy will have a length of L2L by p plus 1, and the pole strength becomes m by q plus 1. So the new magnetic moment will be m into 2L by p plus 1 q plus 1. Clear? So when you cut magnets, that is what happens. Next thing, combination of magnets. What happens if you start combining different magnets? Let's say we have a magnet M1. You combine this with another magnet M2. Now they're just like vectors, like dipoles. How you did, you can do this. You can treat them as two vectors, M1 and M2. So this will give you the resultant. Root over M1 square plus M2 square plus 2 M1 M2 cos theta. They just add up like vectors. There, so if you combine magnets, that's what happens. But there's one theoretical thing here. Even though we say the North Pole is on the right side or left side, whatever, the North Poles are not exactly on the surface. The North Poles are actually slightly inside. The North Pole and the South Pole are kind of inside. Not slightly, they're actually decently inside. The length is actually 5/6 of a 12. This is your magnetic length. So we say, when we say 12 is the length of the magnet, we're actually talking about this 12. We actually ignore this. So if they don't mention anything, take it as a regular 12. But in a CET kind of a question, they'll ask you, what is the geometrical length and what is the magnetic length? So the pole strength is actually, magnetic moment is M into 5/6 12. Most of these things, so the poles are inside the magnet. They're not on the surface. Okay. Next thing, now Earth magnetism is removed from the portion, but in there is one topic which we need to know, angle of dip. You must have heard this term. Even when we did EMI questions, there were a few questions even in HCV or booklet, angle of dip. So what is this angle of dip? Or dip angle? The symbol is delta. So this is the angle made by the Earth's magnetic field with the horizontal. Straightforward definition. Now, if you look at the Earth ka field, it is actually a little weird. Earth ka North Pole is actually the South Pole. South Pole is actually the North Pole. Think about it. If you take a magnet, the North Pole should get attracted towards the Earth ka South Pole, isn't it? And South Pole will get attracted to Earth ka North Pole. The opposites will attract. But initially, right, when some guy was doing whatever experiment, he took out a magnet, he saw the North Pole is pointing in some direction, and they thought that is Earth ka North Pole. So be careful there. So if you look at this is your south magnetic pole, but this is geographical North Pole. So Earth ka actually the magnetic south is towards the north and magnetic north is towards the south. And these two are also actually not exactly same. There's an angle of 12 degrees. You need to understand how are we getting Earth ka magnetic field. The Earth ka magnetic field comes because of Earth ka core. If you see the Earth ka core is molten, it is almost 6,000 degrees. At that temperature, right, the electrons don't stay in the orbits. The electrons are pulled out from the atom. So what you have is something like a plasma. It is like a soup of charged particles. And when this core is rotating, these charged particles are also rotating. And when charged particles rotate, they behave like current loops, and current loops generate magnetic field. So the reason we're getting Earth ka magnetic field is because of this core ka rotation. If the core stops rotating, Earth ka magnetic field will vanish. And same reason why Moon does not have a magnetic field, because Moon ka core is actually a dead rock. Moon, there is no molten core. That's why it doesn't have a magnetic field. So one of the main thing, right, for a planet to have a magnetic field is that core. The core should be hot enough and it should be rotating. And another thing is the Earth ka crust is rotating in one direction, the core is rotating in another direction. Meaning, just to give an analogy, right? Think of like the egg and the egg inside the yolk. If you ever seen a raw egg, the shell is your crust. The inside that yolk, whatever is there, is your core. Now, if you're a Jain and if you've never seen an egg, so yeah, sorry, I can't do anything about this, but figure it out. Right? So there, it is kind of like that. And this thing, right, is rotating. And this north and south pole, right, are not fixed. People have observed in the last 78 years, right, this north pole has shifted by around 150, 200 kilometers. So this north and south pole are moving continuously. So the current estimate, right, this is called magnetic reversals. Every few thousands of years, the north and south pole will reverse their directions. And this is a continuous process. And the way it is going on, the north pole, south pole, the north south pole, right, will going to come near somewhere near Florida, the West Indies area, and the south pole will come somewhere towards Australia and New Zealand. Something of that sort. It is rotating. So that means now see, when you take people on the earth, now for us, what is up, horizontal and vertical? For us, simply up and down is away from the earth and towards the earth, isn't it? So if you look at the magnetic field lines that are coming through, so the field lines, this is your north pole, this is your south pole. So field lines are actually coming like this. This is how the field lines will be. So now if you take a person and make him stand here, what is up and down for you? So this is your up and this is your down, isn't it? This is your vertical. Away from the center is vertical. This is your horizontal. And if you look at your magnetic field, this is magnetic field is in this direction. This angle is called the dip angle. So when you're standing there, every person will see the field in the different directions. So if you look at the field, this is the vertical component of the Earth ka field. This is B and this is your B horizontal. This angle is your dip angle. The tan delta is B vertical by BH. We are more interested in the BH. Because, the question will be like this. A train is going with a speed V on a railway track and the distance between the rails is 1 meter. And the magnetic field of the earth at that point is some 10 power minus 4 Tesla and the dip angle is 60 degrees. Then they'll ask you find the EMF generated between the rails. You must have seen something of that sort. Now, if you see this question, right, that means the two rails are there. The train car rod is there. Rod is going with V. This is the length L. So you need to use BLV. B will be which direction then? B should be perpendicular, na? So there should be B vertical, isn't it? There are two components. There is a B horizontal and B vertical. B horizontal will not create the EMF. So the question is, they'll give you the magnetic field and the dip angle, and you'll not understand like what is the dip angle there. So it should be actually B sine delta into L into V. That is the EMF induced across the rails. Clear? So for that sake, you need to know what is a dip angle and all. So it's just an information there. This is the horizontal component of Earth's magnetic field. So there was a question like this in CET once. So they said there's a person standing, they gave a picture like this, and they said this person observes the magnetic field lines are going into the earth. In which hemisphere is he standing? North hemisphere, south hemisphere, western hemisphere, eastern hemisphere. You can look at the picture here. So for a person who's standing here, what will he think? He will think the lines are entering into the earth. Person who's standing here, he will see the lines going away from the earth. So this guy is standing in northern hemisphere. So think about this. The Earth's magnetic pole is in the northern hemisphere. So the field lines will enter the south pole and leave from the north pole. And that is a CET question. Now, if you don't know this much, right, you guys will think like, what the hell is he talking about? This is one important thing. So when you see this Earth's field, right, east, north, south, and west, this BH actually goes from south to north. Just remember this much. Obviously, right, because the north pole is in the south, the field lines will go from south to north. As long as you remember that the Earth's south pole is in the north and north pole is in south, you'll be able to figure out most of the stuff. Clear with this? That's a little about the magnet. So next class, when we catch up, we will do. There is a more theory, but there are some important ones also. Moving coil galvanometer, right? We will see that working and all. And then we have something called vibrational magnetometer. And then we'll see magnetic materials, paramagnetic, diamagnetic, ferromagnetic, all that stuff. Again, there's quite a bit of a theory there. So mostly next class, we will finish off magnetism also, and then we'll start off with optical instruments. So you have time till Monday. Try to finish, semiconductors by next week, at least as much as you can. Again, I'm telling you, you will not get time to do these things again. So this 1 or 2 weeks when I'm finishing off the chapter, parallelly finish off with me. But if you think, sir, it is overwhelming, itna mera saath nahi ho raha hai, then I would suggest at least finish off 2025 and 2024. 2 years ka to finish kar lo. That way, what will happen? At least you'll remember the basics and all. Maybe next month in November end or December, once you get little free, then you can keep doing 2023, 2022, 21. Slowly you can do. I want you to do from 2020 to 2025. Kafi. If you can do this much PYQs, it is sufficient. No need to do all that 1,000-year-old PYQs and everything. Last 5 years is sufficient. Getting it? So if you are not getting time, compulsory at least 2 years ka finish it off. Neito, you'll forget everything. After a month, this whole thing will look like, something Greek and Latin. It becomes very difficult to cover up then. You start getting scared like, array means nazdik aa raha hai and I don't know what to do. Karke. So don't get into